The latest image of the interstellar object 3I/Atlas, released just recently, offers an intriguing snapshot of this mysterious visitor from beyond our solar system. Captured on November 5, 2025, by the Lowell Discovery Telescope in Arizona, the image was taken when 3I/Atlas was situated 138 astronomical units from the Sun and 223 astronomical units from Earth. At this distance, the object appears in the photograph as a bright, condensed point of light, similar in size to the telescope's point spread function, which is essentially the smallest detail the telescope can resolve. Surrounding this luminous core is a faint halo, reminiscent of a thin atmosphere or a weak cometary coma. While such a glow could point to escaping gas or sublimating material, there is no definitive sign of the kind of elongated dust tail typically associated with active comets. This absence is especially notable considering the camera used a green filter tuned specifically to detect diatomic carbon molecules, or C2, a common tracer of cometary activity. Interestingly, the atmospheric glow around the object appears brightest when observed in the bluest available filter, which hints that some degree of gaseous emission may indeed be present, even if it is not accompanied by a visible dust tail. The lack of a clear tail is scientifically surprising, especially when contrasted with NASA's Jet Propulsion Laboratory report indicating that 3I/Atlas is experiencing a measurable non-gravitational acceleration. Such accelerations in comets almost always arise from jets of vapor or dust being expelled from the surface, as the Sun heats the nucleus. When this material shoots outward, it acts like a tiny thruster, subtly altering the comet's trajectory in ways that cannot be explained by gravity alone. Because the JPL data points to a significant level of such acceleration, one would expect that 3I/Atlas must be losing material at a noticeable rate. In fact, based on the physical principles of momentum conservation, calculations suggest that if 3I/Atlas were a natural comet, it would have had to shed more than 13% of its total mass during its close pass around the Sun. A mass loss of that magnitude should produce a very prominent coma, composed of dust and gas, which would then be shaped by both solar radiation pressure and the solar wind. As these forces push the expelled particles outward, they typically form the iconic tail stretching away from the Sun, a hallmark of cometary behavior. However, no such tail is evident in the latest Lowell image, raising important questions about the true nature of this interstellar object. Of course, the interpretation of the image must take into account the geometry of the observation. When the photograph was taken, 3I/Atlas was located only about 13 degrees away from the Sun in the sky. 4 ground-based telescopes on Earth. This is a challenging angle because it positions the object very close to the Sun's glare and places the observer almost directly behind the hypothetical tail. If the comet's tail, whether dusty or gaseous, is indeed extending directly away from the Sun, as cometary tails normally do, then this observation angle causes us to look nearly straight down the length of the tail. From such a head-on perspective, even a substantial tail may appear severely foreshortened, lacking the dramatic length and structure typically seen when the tail is viewed sideways. Essentially, a tail that might stretch hundreds of thousands of kilometers in space could visually collapse into a compact glow in the image, making it difficult to recognize or distinguish from a normal atmospheric halo. Yet, similar geometrical constraints were present in previous observations, and in those cases, a tail-like feature was still detected. For example, the Hubble Space Telescope imaged 3I/Atlas on July 21, 2025, under almost the same viewing conditions, with only a 10-degree separation from the Sun. Despite this nearly identical geometry, Hubble's sharper imaging capabilities revealed a distinct anti-tail, a structure extending toward the Sun rather than away from it. Anti-tails occur due to the way dust particles, released earlier in the comet's orbit, align along the orbital plane and appear to point sunward from the observer's vantage point. In Hubble's case, the anti-tail was sufficiently pronounced that the object appeared elongated by a factor of 2 in the sunward direction. This stark difference between the Hubble observations and the new Lowell image deepens the mystery. If Hubble could detect dust structures under similar angular constraints, Why does the Lowell Discovery Telescope image show no comparable elongation or tail-like formation? Is the object now less active, or did something fundamentally change in its behavior after perihelion? These questions may soon be answered as observational conditions improve. Over the coming weeks, 3I/Atlas will drift farther away from the Sun's position in Earth's sky, increasing the separation angle to several tens of degrees. This wider angular distance will allow astronomers on Earth to view the object more clearly from the side, making any tail that exists far easier to spot. If a dust or gas tail is present, even a faint one, these future observations should reveal its shape, structure, and orientation with much more certainty. Detecting a tail or confirming its absence would play a crucial role in unraveling the physical processes shaping 3I/Atlas, especially during and after its passage near perihelion. During that close approach, the object would have been subjected to an intense solar energy flux of about 770 watts per square meter. This level of solar heating is strong enough to trigger sublimation on most cometary surfaces, especially if the nucleus is composed of common volatile materials such as water ice, carbon monoxide, or carbon dioxide. Therefore, if 3I/Atlas truly contains such volatiles, then a tail should logically have formed unless some other unusual factor suppressed the normal cometary response. The absence of a visible dust tail despite significant solar heating and reported non-gravitational acceleration leaves room for several interpretations, each with its own scientific implications. One possibility is that the object is shedding gas, but very little dust. Some comets are known to exhibit predominantly gaseous comet with minimal dust output, though such cases are relatively uncommon. Gas-only jets could still exert enough force on the nucleus to create the observed acceleration without producing the kind of reflective particles that form bright tails. Another possibility is that the surface of 3I/Atlas might be unusually resistant to dust release, perhaps due to its composition, structure, or evolutionary history in interstellar space. Being an interstellar object, 3I/Atlas may have undergone surface processing unlike that of ordinary solar system comets, such as space weathering, cosmic ray bombardment over millions of years, or thermal metamorphosis from passing near other stars. These processes might alter the material strength, porosity, or cohesion of its outer layers, reducing dust emission even when heated. Alternatively, it is conceivable that the mass loss implied by non-gravitational acceleration does not stem from sublimation at all. Some researchers have proposed that unusual acceleration patterns observed in previous interstellar objects might originate from mechanisms unrelated to gas jets, such as outgassing of exotic materials, delayed thermal desorption, fracturing events, or even radiation-driven forces acting on highly reflective surfaces. While most such explanations remain speculative, the unusual nature of interstellar objects leaves the door open to non-traditional interpretations. If 3I/Atlas indeed behaves differently from typical comets, understanding those differences could yield valuable insights into the diversity of small bodies that exist in other planetary systems. As scientists await clearer data from future observations in the coming weeks, the new Lowell image adds an intriguing piece to the puzzle rather than resolving it. The conflicting indicators, non-gravitational acceleration without a visible tail, a faint atmospheric halo with no clear dust signature, and viewing geometries that both obscure and reveal different features at different times, highlight the complexity of studying interstellar visitors. Each new observation offers clues, but also raises fresh questions. Meanwhile, public awareness and scientific curiosity continue to grow, reflected in the hundreds of messages and letters that enthusiasts have been sending in response to the latest developments. These reactions underscore how deeply the discovery of interstellar objects captures the imagination, blending cutting-edge astrophysics with the sense of wonder that comes from witnessing something literally not of this world. As we await the next round of data, astronomers remain focused on unraveling the true nature of 3I/Atlas, knowing that each new observation may bring us one step closer to understanding the origins, behavior, and mysteries of this remarkable traveler from beyond our solar system.